Zinc-Carbon. Zinc-Carbon batteries were the first commercial dry batteries. And for a long time, they were the only option you could buy at a RadioShack or a local hardware store. They were created because people needed a portable power source for flashlights and early radios. However, Zinc-Carbon came with a massive problem. They had very low energy capacity, meaning your device would die very quickly. But what made it worse was the construction. The outer can was actually made of zinc, which served as the negative electrode. So as the battery worked, it literally ate its own container. That is why, if you left these batteries inside a toy or a remote for too long, they would leak acid everywhere and destroy your electronics. It was a nightmare for anyone growing up in the 80s or earlier. Alkaline. Alkaline batteries became popular in the 1960s and 70s as a major upgrade from the leaky Zinc-Carbon. You know them today as the standard Duracell or Energizer batteries you buy in bulk at Costco. Alkaline was created because gadgets were becoming more power-hungry. Things like the original Game Boy required 4-ish AA batteries, and if you used the old zinc ones, you'd maybe get an hour of playtime. Alkaline solved this by packing much more energy density into the same size, allowing kids to play Tetris for hours. However, just like Zinc-Carbon, alkaline is a primary battery, meaning once it's dead, you have to throw it away. This created a massive amount of e-waste in American landfills. And buying a new pack of batteries every week for your Walkman or Game Boy was getting really expensive. That is why the world needed a rechargeable solution. Lead acid. Lead acid is actually ancient technology, invented back in 1815, but we still use it today in almost every gas-powered car in America, like your Ford F-150 or Toyota Camry. The reason we still use it is simple. It can deliver a massive burst of power instantly, called cold cranking amps, which is exactly what you need to start a frozen engine in the middle of a Chicago winter. However, lead-acid batteries are incredibly heavy and contain toxic lead and sulfuric acid. That is why they are only used to start the car, not to power it for long distances. If you tried to build a modern electric car using lead-acid batteries, the car would be so heavy it would barely move. NECID nickel-cadmium. NICEAD came out as the first mainstream rechargeable battery for consumer electronics. This was the era of those bulky cordless drills and the massive camcorders you see in old home videos. The great thing was you could recharge them. But NICEAD had a very annoying problem called the memory effect. Basically, if you recharged your drill when the battery was still at 50%, the battery would forget it had the other 50% and eventually act like a smaller battery. So to keep them healthy, you had to fully drain them every single time, which was super inconvenient. Plus, cadmium is extremely toxic, so getting rid of them was a major environmental headache. NIMH nickel metal hydride. NIMH came out in the late 80s to fix the problems of NICEAD. You probably know these as the rechargeable Panasonic Eneloop batteries photographers love. NIMH offered much higher capacity, up to 2 or 3 times more than NICEAD, and more importantly, they significantly reduced the memory effect. This meant you could charge your digital camera batteries whenever you wanted without ruining them. However, they weren't perfect. Early NIMH batteries had a high self-discharge rate. If you charged them and left them in a drawer, they would be dead a month later even if you didn't use them. While newer versions fixed this, they were still too heavy for the next big revolution: smartphones. Lithium-ion. Lithium became the commercial standard in the early 90s, and this is the technology that truly changed the world. It was created because devices like laptops and the original iPod needed to be light and run for a long time. Lithium batteries are incredibly lightweight and have a very high energy density. Without them, the iPhone would probably be the size of a brick. However, lithium is also very volatile because the liquid electrolyte inside is flammable. If the separator inside the battery fails, it causes a short circuit and leads to thermal runaway. A famous example of this was the Samsung Galaxy Note 7, which was banned by the FAA on all US flights because they kept catching fire. That is why the TSA is so strict about not putting loose lithium batteries in your checked luggage. LiPo, lithium polymer. LiPo is a slight variation of Li-ion that became popular as devices got even thinner. Instead of a liquid, it uses a polymer gel electrolyte. This allows manufacturers to shape the battery however they want. It's what allows the MacBook Air to be so thin, or a drone to carry a battery without being weighed down. But the trade-off is that LiPo batteries are more fragile. If you've ever seen an old iPhone or a laptop where the trackpad pops up because the battery underneath puffed up like a spicy pillow, that's a LiPo battery failing. They require very precise charging circuits to stay safe. EV batteries, NMC and LFP. Now, we are in the era of electric vehicles, and the batteries here are just massive versions of lithium technology. There are two main types you'll see in cars like Tesla's. First is NMC, nickel manganese cobalt. This is used in long-range models because it holds a lot of energy, helping you drive from LA to San Francisco on a single charge. But it uses cobalt, which is expensive and ethically controversial to mine. The second type is LFP, lithium iron phosphate. You'll find these in the standard range Tesla Model 3. They are cheaper, safer, and can be charged to 100% daily without degradation, but they have less range. So if you live in a cold climate or do a lot of road trips, battery chemistry actually matters when buying a car. Solid state. Solid state is the future technology that everyone is waiting for. It's expected to replace lithium in the coming years. The idea is to replace the flammable liquid inside the battery with a solid material like ceramic or glass. This would make batteries virtually impossible to catch fire, even if you crash. More importantly, it could double the range of EVs and allow them to charge in like 10 minutes, basically the same time it takes to fill up a gas tank. Toyota and other giants are racing to get this out, but it's still very expensive to manufacture right now. Anyway, the point is, battery technology has come a long way from the leaky zinc cans that ruined your toys to the solid-state future that might power your next car. I also made some other cool videos about how CPUs and RAM work, so don't forget to watch them later, okay?